So once again, my name is Ian Treviranus. I am the Product Line Manager for Particle Characterization Solutions. It's a very complex title. Basically what it means is I'm the guy in charge for a lot of what goes on in the Americas for these products. I'm here to talk to you today about laser diffraction, give sort of a broad-based introduction. We're not going to go into anything too deeply. It should be very informative, not very commercial, I hope. And we're going to cover everything from fundamental principles all the way up to practical everyday uses, how you can maybe get a little bit more out of your analyzer. If you need to contact me, my email is on the first slide, or visit our website. The easiest way to get there is go to horiba.com/us/particle. So here's the plan of today, a plan of attack for today's presentation. We're going to cover how does laser diffraction work, what it can do for you, how does that ultimately help you do your job better? What are the strong points, and more importantly, what are the weak spots? A lot of times vendors don't like to focus so much on what the weak points are, but they're important to understand. And then we're going to finish it off with a Q&A. But the first thing we're going to do is we're going to talk about how it works. So here's the core principle. If anyone ever challenges you, how does this big box work? It basically comes down to we can investigate a particle with light and derive its size. If we consider this to be an ideal point scatterer, we're hitting it with some well-behaved column of light, and the light is hitting it on the edge. This is called edge diffraction. It's creating waves, and somehow we can study the overlapping interference pattern and derive a particle size distribution from it. This is the very core principle. We can do this because the angle and intensity of the scattered light depends on that size. So larger particles have, you'll have to bear with me here a little bit, but larger particles scatter at narrower angles, which in this case means the target is a little bit smaller, and it also scatters light much more intensely. So the color red is much brighter than, let's say, a small particle, which scatters over a wider range of angles. The target is a bit bigger, but it also scatters less intensely, so the color red is a little bit lighter. That's the fundamental relationship. Larger particles scatter at smaller angles and more intensely. Smaller particles scatter at wider angles and less intensely. So then essentially all we need to do this measurement is we need a light source, a particle, some light detectors, and a German mathematician. And we can use one of two of them. We can use either Joseph von Fraunhofer, who developed the Fraunhofer approximation, or Gustav Mie, who developed the Mie scattering theory. This is a little tongue-in-cheek, but the important thing to take away here is that Mie scattering is ultimately a better solution for most particles. We'll see in a second that it extends the measurement range down into the nanometer scale, whereas the Fraunhofer approximation starts running out of steam right around, well, it depends on the wavelength of light, but we usually say between 20 and 50 microns. So this is a little bit tongue-in-cheek. It's just sort of interesting that they're both German mathematicians. All right, so there's four different types of interaction between light and particle. We have diffraction, refraction, reflection, and absorption. And the first two are the good ones. We like diffraction and refraction because it gives us useful information. We can tell something about the size of the particle from those two pieces of information. Diffraction, we can also call edge diffraction. It's where the light hits the edge of the particle, tangential surface, and it changes angle and it changes intensity. So that's, again, at the very fundamental core principle of how the measurement works. Refraction becomes important when the particle size becomes smaller, some multiples smaller than the wavelength of light. And that's where the light passes through the particle. It changes angle a few times, changes intensity a few times, and we can collect that information as well. We don't like reflection and absorption simply because it's where we lose the signal. Reflection is where the light hits the surface of the particle and reflects back. An easy mental example is something like gold dust. We don't like it because this has very little meaning for size. So yes, it's possible to collect reflected light on our light detectors, but it's not really giving us any useful size information, so it's actively working against us. Now we have a few ways to counteract that. The Mie scattering theory gives us something called an imaginary component of the refractive index that we can use to help correct for these poor light interactions. Not really a great term, but it gives us a tool to correct for it. Absorption is also not good because the light's basically entering the particle or being absorbed at the surface, and it's not really doing anything. Worst case scenario is it's being re-emitted through some sort of fluorescence or phosphorescence. Usually what happens is the light gets absorbed and it gets re-radiated as infrared heat. So if you imagine running paint pigments or carbon black, something that's going to absorb a lot of light, really what you're doing is you're hitting it with light that's being absorbed. You know, if you're running a blue pigment, it's going to be absorbing all the light that's not colored blue and re-radiating it as heat. So we like diffraction and refraction. Those are useful. Reflection and absorption work against us, but we have tools to correct for them. So again, here's our basic mental model. We have a point scatter in space. We have some well-behaved column of light hitting it. Typically, in modern laser diffraction analyzers, this is laser light. Hits the edge of the particle, and it begins creating interference patterns. Basically, it creates waves off of the two-point surfaces here. And the waves begin to overlap. And it's hard to do, but if you could sort of reach into the screen, take this image and rotate it so that you were looking at it head-on, this is what we would see. You know, this in the center here is our point scatter, and we see radiating lines of minima and maxima. So what we're really measuring with a laser diffraction analyzer is a diffraction pattern. We'll also call that a light scattering pattern or a scattered light distribution. There's a lot of different names for it. But it depends on the shape of the particle. We'll talk about that a bit more in a bit too. But if you have a perfectly spherical particle, you'll get a very well-behaved, very nice-looking diffraction pattern. If you have, again, a very well-behaved rectangular prism, you'll get another well-behaved diffraction pattern. But if you have a more realistic-looking particle, something that is very hard to describe using shape terminology, then you'll get sort of a mismatch diffraction pattern. And this is much more the realistic case. So more often than not, this is what your analyzer, or this is what the laser diffraction analyzer is measuring. And it has to back out some shape measure from this. So why do we call it a light scattering pattern? I talked about this maybe 2 slides ago. Essentially, you have light impinging on some edge. It creates waves. The waves overlap. And one way of visualizing this is an intensity distribution of fringes. So you'll have some areas where the waves overlap constructively. You'll get maximum light intensity. And some areas where the waves overlap destructively, and those will be local minima. So you get areas of bright light, areas of almost no light, and it repeats in a sort of uniform way if the particle is, again, well behaved and of a nice, clean shape. This happens regardless if, I should say, I neglected to mention that this all has its core at Young's double slit experiment, where Young created 2 slits in a piece of paper. It's not really paper, but we can think of it that way. Shone a light at it, and he noticed that there was this distribution of fringes, this diffraction pattern. The point I want to make on this slide is it doesn't really matter if it's a double slit or a single slit. Really what matters is that the light is interacting with an edge. And in fact, it doesn't matter if it's a double slit, a single slit, or we can imagine a single slit as being a particle. It's really just the edges that matter. If you were to look at the intensity distribution, they are slightly different between here, but we can back that out using some mathematics. But an easy way to think about it is it just boils down to the same thing. The light is hitting the edge of something, and it's creating interference. The size of the particle, or the size of the slit, also affects the angle at which the light is scattered. So in this case, a larger particle will scatter at narrower angles than a smaller particle, which will scatter at a wider angle. So it may be a bit hard to discern in this slide, but this is a smaller angle than this. This is wider. And that's a fundamental relationship, that the size of the particle is related to the angle of scatter, and it's also related to the intensity of scatter. Other factors that affect the intensity distribution or the light scattering pattern, in addition to size, we talked about shape a little bit, but also optical properties will affect the angle and intensity of scattered light. And this is where we start needing to use the refractive index. How is light passing through the particle? It turns out in practice to be extremely difficult to extract shape information without a priori knowledge. So if we can back out a particle size distribution from a diffraction pattern, we can't really do that for the shape of the particle unless we know ahead of time that it's a column of 6:1 aspect ratio. If you know that ahead of time, you can sort of back that out, but it's very difficult. So what we do in order to get a solution is we assume that it's a hard sphere. Every particle is a hard, non-porous, spherical particle. It simplifies the mathematics. We can solve it completely. It does add some error, but it's how we do the measurement. Optical properties, as I said just a second ago, basically that means refractive index, and it helps explain refraction. This is also the key difference between the Fraunhofer approximation and the Mies scattering theory. This is why Fraunhofer sort of runs out of steam around 20 microns, and Mies can be carried through into the nanometer regime. So that was just a little bit on how it works. At the end of the presentation, I'll have several previously recorded webinar references so that if you'd like to learn more about diffraction theory, we have webinars up on our website that'll tell you more about it. Now we're going to move on to what can this measurement do for you? I'm sorry, what are the limits is a better way of thinking about it probably. So one of the reasons diffraction has become so very widespread and popular is because it's a very, very flexible size analysis. And the largest part of that is it can measure so many different sizes of materials. You have other light scattering techniques like dynamic light scattering that are really just nanoparticle only. There are ways of extending it up above a micron, but it really begins to run out of steam pretty quick. Laser diffraction, on the other hand, can go down as far as 30 nanometers and up as far as several millimeters. It's a wide, very, very wide dynamic range. So we see that it works for nanoparticles, small micronized particles, and then large micronized particles. And I include these graphs here. You know, this is really what's happening. You have a small particle. If it's small enough, the light is going to interact with it, and it's going to scatter light essentially isotropically, depending on how big it is. This is also known as a Rayleigh or Rayleigh, depending on your pronunciation, scattering. If it's a small micronized particle, most of your scattering will still be in the forward low angle regime, but you'll start to see differences on these, I guess we would refer to them as side angle or side scattering. And then as the particle gets larger and larger, more and more of its light gets scattered in the forward low angle direction, and we don't care so much about these other angles in the back or the side. Diffraction is also flexible in the sense that it can measure many different types of materials. It can measure suspensions, which are solid-liquid interfaces. It can measure powders, which are solid gas, or emulsions, which are liquid-liquid. So it really covers a wide range of gamuts. It, in fact, can also measure creams and pastes using the right accessories as well. So again, it has a very wide dynamic size range. It can measure multiple sample types. We don't really need any a priori information to monitor the size change. We can use the refractive index to help improve our accuracy for particles less than 20 micron, but we don't really need it to be able to tell that the size distribution is changing from batch to batch or formulation to formulation. It is a very, very fast measurement. You should think of it in terms of seconds and not minutes. A lot of other technologies, X-ray sedimentation, for instance, can take minutes, if not almost an hour for very small particles. Dynamic light scattering is usually 1 to 5 minutes measurement. Image analysis is usually minutes measurements, so diffraction is just about the fastest thing on the market. But practically, it's also very easy to use and very easy to interpret. You know, that's a large part of why you should want to choose an analyzer. Is not only is it a good fit for the type of measurement that you want, but it's something that anyone can walk up to, pick up with maybe half day or a full day's training and just run with it. And something that maybe we don't talk about often enough is that laser diffraction is a first principle measurement, which essentially means that we don't need to calibrate it. We don't need to teach the analyzer what is the correct size and what's not the correct size. And the reason that's important is it doesn't fall out of calibration. The instrument is either working or it's not working. And that allows us to have a little bit greater peace of mind with the results. So diffraction has been proven to have very, very good sensitivity to nanoparticles. The Horiba LA950, I think, is still the only analyzer that can measure down to 30 nanometers. And it does that with a red and blue light source setup, so 2 light sources. And we measured colloidal silica. This is Ludox TM, and it came in at a median size of around 30 nanometers, which is fairly close to what is on the bottle. We can also measure polystyrene latex size standards, 40, 50, and 70 nanometers in addition to 30 nanometers. And it can distinguish between them too, right? It's an important distinction that if something is a different size, it doesn't just give you the same number, right? That's not really an accurate result. That's a lack of resolution. So it has some decent resolution underneath 100 nanometers. It's not as good as the resolution you can get up above a few hundred nanometers, but it's decent enough. So diffraction has good success even with nanoparticles. And I include these 2 images down below just to show you the effect of having the blue light source. So there are different solutions out on the market. Some people will use 3 lasers. Some people will use different ways of polarizing the light. But a very typical setup, certainly in Horiba and some other vendors, is to use a red laser and some sort of blue light source. In the Horiba LA950, we use a blue LED. And the effect is basically sensitivity. It's the resolution for very small particles that I was just talking about. So in this graph, if all we use is a red laser diode at 650 nanometers, we can't really distinguish the scattering pattern between 50 and 70 nanometers. They overlay almost perfectly. If, however, we investigate the 50 and 70 nanometer particles with a blue light source, a 405 nanometer LED, we can begin to see differences. Diffraction also is probably the only, if not the only, then it's the best technology to use when you're looking for very small particles that are also in the presence of large particles. I talked very briefly a few seconds ago about dynamic light scattering. If all this sample was something that ended at about 800 nanometers, then it would probably be a good sample for dynamic light scattering. But there are other particles in here that extend up to 8 microns, and that sort of rules it out for other light scattering techniques. In this specific example, we're looking at some cosmetic creams that have particles that are less than 100 nanometers. And there's some concern, there's always a little bit of concern. Are there any dangers for nanoparticles if you put it on your skin? Can it get into your bloodstream? I'm not commenting as to whether or not that's a real concern, but it's a measurement that some of our customers have made, and it's very much a diffraction-only application. But it's not just nanoparticles that diffraction can do. It can do the whole range in between. Here I'm highlighting its ability to measure very large particles. These is coffee results, different grinds of different types of coffee. And here we see a result all the way up to 3 millimeters. We're not seeing the entire tail of the distribution, so there are some materials that are a bit larger than 3 millimeters. But basically the trend is with every new generation of diffraction instrument, if the manufacturer, someone in my position, let's say, if we want to make the case that we have the best technology on the market, the best performance, one of the ways you try and prove that is by extending the range of measurement. So with the 950, with the LA 920 and 930, we used to be able to measure up to 2,000 microns. Now with the 950, we can measure up to 3,000 microns. And there are real applications up there. Here in the bottom graph, we're seeing, I think these are, 3 millimeter alumina balls. So we do have customers that measure at the extremes of the distribution. And, depending on how the sample's set up, this could really only be suitable for diffraction. When you get into the large area, it could be more suitable for other techniques. This is capable of being sieved. It's also capable of being analyzed using image analysis, but many times it's still diffraction only. Another advantage of laser diffraction is it's very flexible in terms of sample handlers. I was saying earlier that you can run emulsions, powders, suspensions, creams, and pastes. Well, you can do that because we have a wide range of sample handlers. If you have only a very limited amount of sample, you might run it on a cuvette type accessory like a fraction cell. If you have a paste, you'd run it on something like the paste cell. If you had many different types of materials or just a very high volume of material, you might run it on some sort of auto sampler or slurry sampler. Or if you had a powder, you might run it on a powder accessory. For the LA950, we call ours the powder jet. And it's basically you just put the powder directly on the chute, it introduces it into the measurement zone, and you get your measurement. Very straightforward. And the last point I want to make here is that the technology has advanced to remove a lot of the trade-offs that were present in our industry before. So a lot of times if you wanted to do a dry powder measurement, you had to sacrifice a little bit in terms of precision because typically it's just a little bit more difficult to control how the powder is introduced into the measurement zone. It's just a little bit, it was historically easier with wet sample handlers, but as every new generation gets introduced, the manufacturers make improvements, and now with the LA950 powder jet, there really is no distinction. It's how you want to make the measurement. If you prefer to measure dry because that's its native state or that's how it's going to be used as the final product, you can measure dry and feel very confident you're not losing anything. All right, so the next section we're going to cover is how does this practically help you? So very basically, diffraction can help you monitor your process performance or your product performance, and then sometimes you can do both. So the example I have here for you is from a paint company that owns an LA950, and if you've ever looked at paint or if you've ever thought about paint, you know that it's a very complex material. It has lots of different things added to it. It's going to have pigment, it's going to have stabilizers, it's going to have spacers, it's going to have all sorts of different polymers and resins, and it's very complex, which is typically a challenge for diffraction if you care about knowing exactly what ratios are in the material. But if what you really care about is knowing that this was a good paint batch and that's a bad paint batch, diffraction is perfectly well suited. You don't have to care that the pigment might have a different refractive index than the polymer resin, might have a different refractive index than the aluminum trihydrate spacer. You just choose one refractive index, find empirically a good batch of paint, measure it. You might measure it many times to set up an internal standard, and then you measure everything else the same way and just compare it against it. So in this example, the black result is our internal standard. That's this user's definition of a good paint batch. The red was another batch of paint that they qualified as passing. Even though there's a slight difference here in the coarsest particles, they, from other tests that they do, decided that this wasn't important. This could just be a dispersion issue in how they added the sample into the LA950. But the big catch was this blue line here. And this is all the same paint product, mind you. But the blue line was able to highlight a very big problem for them in production. They had completely missed the amount, missed on the amount of material, a certain material that I actually don't think I'm allowed to say, but a certain material that they were supposed to add. So the graph was able to very quickly show that they didn't have enough of that material in the analyzer or in the final paint, and the analyzer was able to tell it to them. And all of this was accomplished even though it was a very complex product formulation. So we would call this like a thumbprint technique. So they took a thumbprint of what a good batch was and they just compare back to it with every subsequent measurement. And that's been very successful for them. But if instead it's not just the change in process, but the actual product performance itself that you need to measure, diffraction has a lot of success there too. Here I'm showing a Cnp Slurry example. And if you know anything about Cnp slurries, that stands for chemical mechanical polishing. There are a few problems that people who are in the Cnp business want to avoid. And one of the big problems is they really need to avoid these large particles. Because if you're trying to polish something, If you have a large particle in there, it's going to scratch up whatever it is you're trying to polish. And if you're in a semiconductor industry, that could be very, very, very expensive product rework costs. So they're very heavily invested in making sure that if there are any large particles in there, that whatever technology they're using to determine particle size can detect them. So in this case, it was this was actually an experiment that I designed a few years ago. It was a base Cnp slurry that I started adding other silica particles to of a known size. And by the time I got to 0.05 weight percent, which is a ridiculously low number, even for diffraction, the LA950 was able to pick it up. So even a very, very small percentage of outliers, diffraction, the technology has been proven it can pick it up. And almost as importantly, especially for the CMP application, it was able to correctly place the main distribution as well. So this is the other factor that a lot of CMP companies care about, is where is the main distribution and are there any large particles? And in one measurement, laser diffraction was able to tell you both. I say here below that diffraction is resolution limited, and that's generally true. And what that means is if the first peak here is at a median of 31 nanometers, if I mixed in another material that had a median at 40 nanometers, diffraction wouldn't be able to give you baseline resolution between them. In fact, that's probably putting it kindly. It would most likely give you one peak that's a mix of the 30 and the 40 nanometer material. And that's what I mean by resolution limited. It's not measuring every single particle. And because it can't do that, because it's measuring an ensemble of particles, you just have limited resolution. One of the other things diffraction can do is if you only have a very small amount of sample and you know you need to do some sort of particle size analysis on it, diffraction technology is advanced to the point where you can really minimize how much sample you need to add to get a reliable size result. I'm sure when the first laser diffraction analyzers were produced, the signal-to-noise ratios of the instruments weren't as good as they are today, which basically means you need to add more sample. As you add more material, you'll generate a higher intensity scattering signal. Regardless of the size of the particles, as you add more light will scatter. And that'll improve the poor signal-to-noise ratio, and you'll get a measurement. But as each new generation of technology is unveiled, the signal-to-noise ratios typically get better and better if the design is being updated. Sometimes the design isn't updated, it's just the box covers. But if the design is being updated, that should be a central goal, is to make it easier to get a good measurement with less material. And in this case, again, this is data that I collected a few years ago on the LA950. Again, showing colloidal silica, which is a very weak scatter. I'm not claiming that the median value here of 35 nanometers is correct. A few slides ago we saw it was 30 or 31 nanometers. But what I'm trying to point out here is that at only 132 milligrams of sample added, we were able to get a result. Now, 132 milligrams is a heck of a lot more than 0.165 milligrams that was needed for a 9.3 micron median. But that has everything to do with the fact that this material is so small, it's scattering so very little light that you need just to add that much more sample to get a result. At about 9 micron median, you're scattering strongly enough, and magnesium stearate as a material isn't exactly an overwhelmingly strong scatterer itself. Many inorganic materials will have much stronger scattering efficiencies than an organic material like magnesium stearate. But even with that said, the 950 signal-to-noise ratio is so good that at only 0.165 milligrams added, we were able to get a reasonably accurate result. And when I say reasonably accurate, I don't mean that if I added a little bit more, this median value would double. It might shift to 9.5 and stabilize there with a little bit more added. But the difference between 9.3 micron median and 9.5 micron for a lot of applications isn't that important. The final example here is a biodegradable polymer. I think it was PLGA. Much larger median size, so just a larger material. And this probably has a weaker scattering efficiency than magnesium stearate. So we had to add a little bit more material, 1.29 milligrams as opposed to 0.165. So the next few slides, I just want to talk a bit about the measurement workflow. I remember from the poll that many of you already use laser diffraction instruments, so this will be a bit like review, but for those of you who are new to the subject, I'm just going to touch on it very briefly. So the basic measurement workflow is you need to do something to prepare the sample many times, whether it's arriving in your lab as a powder or a paste. A lot of times, many samples, many applications aren't ready for direct addition to the analyzer. It's sort of lucky if your application is so easy, because then you can just scoop it into the analyzer and save yourself a few minutes work, but a lot of times you have to do something to prepare it. We have other webinars on our website on how to attain good sampling and dispersion, but that's an absolute must. If you can't be absolutely confident that what you're putting into the analyzer is representative of the sample you have in your lab, then it's going to be a bit more difficult to trust the data that comes out of the analyzer. Sort of garbage in, garbage out, although that's a bit harsh. It turns out that you may need to use a surfactant or an admixture to either get the powder sufficiently wetted or to keep the particles suspended and adequately dispersed. And we just have a few graphics here of what good dispersion should look like. You don't want your material to be sedimented when you add it into the analyzer. If it is, you need to mix it up, make it look more like this. You certainly don't want your material to be flocculating, or if it's an emulsion, you don't want it to be coalescing or creaming. These are not good dispersions. Then you need to prepare the system after you've prepared the sample, and what that basically means is you want to align the laser, align the optical system to maximize the signal to noise. You want to give yourself the easiest possible path towards getting a good measurement. And then you'll want to acquire some sort of background reading, and that's just to remove the sort of instrument noise that's in there. We like to think that the LA950 is a very, very high performance analyzer that uses a lot of high quality parts, but even that, it will still have some background light scattering because we're not outfitting the measurement chamber with light absorbing stealth materials. So there's always going to be some background there, and taking a blank just zeroes it out from the measurement. And the whole alignment blank process probably takes maximum 10 seconds. So once you've prepared the system and the sample, you want to add the sample to the system. And typically we want to add it to some specific concentration range. I'll point out the green bars here. So in the LA950, what you're doing is we're measuring the amount of light that's being transmitted through the cell. So in this case, I apologize if it's a little bit hard to read, but we're looking at about 88% red laser transmission, which means that if 88% of the light is being transmitted, it means that 12% of the light is being blocked. Now, that could either be that it's absorbing or that it's being scattered through diffraction and refraction, which is what we want. But you need to add to some specific concentration range. If you add too little, you won't have enough signal to get a good measurement. If you add too much, you'll get into what we call the multiple scattering regime, and that's where light scatters off of more than one particle before it hits the light detectors, and that skews the distribution finer and finer and finer. And most vendors will recommend a typically good concentration range. In this case, we do it with green bars. So long as you're within the green bars, chances are very good you'll get a good measurement. So once you've added enough sample to the analyzer, you want to pump it through the measurement zone. Unless you are dealing with a very small material that has density very close to whatever liquid you're using to pump through the instrument, it's going to settle out over time. And because it's going to settle out, you need to turn on a circulation pump, or if you're doing a dry powder measurement, you're going to turn on compressed air in a vacuum to make sure that everything's moving through the system. Once you have that done, you may want to do some final dispersion. Most systems come with a built-in ultrasonic probe that you can turn on, and the purpose of the ultrasonic probe is that it adds some energy and it can reduce the particle size. Typically we want to avoid milling the particles, we just want to fully disperse them. No agglomerates. Here's a bit bigger image of what the manual measurement screen looks like in the LA950. We see the four most important buttons all on top of each other. Feeding the analyzer means getting some liquid into it. Then you want to align the optical system, take your blank, you'll add your sample, and then you'll take your measurement. Finally, when you take your measurement, you're going to click something usually called the measure button. And the key distinction I want you to take away here is that the hardware measures the scattered light distribution, which is here, whereas the software then calculates that and turns it into a size distribution. So really, all your analyzer is doing, for all the money that you paid for it, is it's just collecting the angle and intensity of scattered light. Then it's a software algorithm that, if it's a modern analyzer, is based on the Mie scattering theory, something that was developed many, many, many decades ago. It's not exactly new technology. That old scattering theory is then taking this and turning it into a size distribution. So really, all of the advancements in your laser diffraction analyzer are just about getting better raw data. How does it create the particle size distribution? I'm not going to go too into detail there. Again, there is a laser diffraction theory webinar up on our website that goes into more detail. But the basic idea is that it's an iterative process. So you calculate some scattered light distribution. You'll compute your initial particle size distribution off of that. It back calculates what the ideal light scattering pattern should be to create this distribution. And then it compares the measured and the ideal light scattering distribution and how different that is. Takes that into account, recalculates the size distribution, and it just keeps going around and around and around like that. So I took you through the basic workflow of a manual measurement. And, if you do a manual measurement, it requires some training. It requires some understanding of what is a good concentration range. How do I know when I'm using a reasonable circulation pumping speed or a reasonable compressed air setting for a powder measurement. But it still requires some training. So one of the things we did with the LA950 is we designed some software called the Method Expert. And the goal of the Method Expert is to walk you through the measurement process, walk you through the method development process, impart a lot of the knowledge that we have inside our company and inside our employees, and put it into the software so that you can feel confident that you've learned some very valuable things about how to put a good method together, and you can feel more confident in the results instead of, many times I'll talk to customers that have a method or a procedure that was written 15 years ago by someone that's no longer with the company, and they're just not sure, is this still appropriate, is it correct, how do I know for certain? Well, that's what you can use the Method Expert for. And there's a few different sections to the Method Expert. There's an area we call measurement optimization that just takes you through how you set up the hardware, circulation pumping, concentration, ultrasonic, and how long the measurement works for. And then there's a calculation optimization section that'll help you pick the correct refractive index components. And the entire goal is to communicate to the user, why are these tests important? Why do these choices matter? What happens during the test? It tells you how the results are going to be displayed, and then how to choose the correct value. And one of the nice things that we've gotten good feedback on is that each test you can choose up to 5 distinct values for testing. Where that's become really helpful is when you want to optimize refractive index. We can create up to 5 different refractive index kernels all at the same time, display the results, the actual size distribution results, display how that affects the D10, D50, and D90 metrics, and also how it affects something we call the R parameter, which you can think of as a goodness of fit between the theoretically perfect scattering pattern and what was actually measured. And a good refractive index should minimize the R parameter. And then at the end of it, you want to make the instrument as easy as possible to use. So you go through all this work of creating a great method, choosing the right hardware parameters, the right calculation parameters. Then we want to build it into some automated sequence that at the end of it, we just put in a single name in, pops out a sequence and condition file, so that all we have to do then is go back to our software, push a button, specify which routine you want to run, which sequence you want to run for which application, and out pops a measurement. All right, so we covered the first 3 topics. Now I want to talk very briefly about what the strong points and the weak spots are for diffraction. And in fact, I'm going to focus mostly on what the drawbacks are for diffraction, because sometimes we don't talk about it enough. So one of the biggest sources of error for diffraction measurement is this assumption that it's a hard sphere. And that really can be problematic when your particle shape gets very, very non-spherical. When it becomes much more like a fiber, much more like a rod, you're building in a lot of error into your distribution. And really all that's affecting is your accuracy. If the size of the rod is changing based on changes you've made to your formulation or your process, the instrument will still be able to communicate that change to you. It's just the accuracy of the size that's suffering, not its ability to describe changes in the final product. But one of the other stumbling blocks is because we're using an equivalent spherical diameter, it makes it very difficult to compare diffraction data to other techniques that aren't also measuring equivalent spherical diameter. For instance, dynamic light scattering measures the hydrodynamic radius. It also makes the assumption that it's a hard sphere, but the hydrodynamic radius isn't the same thing as the equivalent spherical diameter that diffraction is measuring. It also makes it extremely difficult to compare to sieves because sieves are measuring the second smallest size of a particle. Not the smallest size, but it's the second smallest size that can fit through the square sieve mesh opening. And that's definitely not the equivalent spherical diameter. If you're comparing to X-ray sedimentation, that's really measuring the Stokes diameter. Again, not an equivalent spherical diameter. So it's just important to understand the trade-offs. We assume that it's a hard sphere in order to solve the equations. Some vendors will say that they can solve for irregularly shaped particles. That's a bit of marketing spin. Really what it is they're doing different things to the imaginary component of the refractive index, which every vendor should be able to do, because again, that's how you correct for things like shape. It's how you correct for things like absorbance and reflection. We can also think of a drawback in that diffraction requires an sort of quote-unquote optical concentration range. Because you're investigating it with light and because you only want the light to hit one particle on its way through the measurement zone before it hits the detectors, a lot of times you'll have to dilute your sample. If it's a powder, it doesn't really make a difference, but if you're dealing with a very high concentration paste or cream, a lot of times you can run into dispersion issues because dilution can cause stability problems. You have a very nice stable cream dispersion, but as soon as you start diluting it, you get flocculation. Or if it's like a salad dressing emulsion or a liposome emulsion, a lot of times you'll dilute it and you'll get coalescence. So that's definitely a drawback, is that you can't run every concentration through the analyzer and have it work correctly. This is where new technologies like acoustic spectroscopy have really started becoming very popular, because they can measure in the sort of, again, quote-unquote native state where you don't have to dilute. You can measure at much higher concentration levels. So it's become very, very popular for a lot of applications, not the least of which are creams and pastes. And finally, I want to talk to you about diffraction measures on what's called a volume basis. And that gets back to what I was saying a few minutes ago. It's not investigating each particle individually, it's investigating the ensemble. And what that means is the light scattering pattern is related to the volume of the particle that's being investigated. So what you're getting is a size distribution based on that particle volume. So while this is excellent for chemical engineers that we're taught how to do mass balances, you cannot then calculate a number basis without very significant error. So again, if you're comparing this to some sort of SEM result or TEM result or even optical microscopy, where it is definitely a number basis because you're looking at each individual particle, a lot of times the results won't match up. And the main difference is that when you look at something on a volume basis, it tends to emphasize or weight the largest particles because, again, this is just diameter that we're measuring. So one dimension. As soon as you start cubing it to determine the volume, if you have a large diameter, the cube of that large diameter is going to be much larger than the cube of a small diameter. So it emphasizes large particles, whereas a number distribution tends to emphasize small particles because a lot of times you'll have just many, many, many more small particles than the large ones. So it's important to understand that distinction. When you make a diffraction measurement, you're making a volume-based measurement. But there are plenty of benefits to outweigh those drawbacks. We've talked about a lot of these already. It has the widest size range of advanced particle sizing technologies. In fact, the most advanced analyzers can measure down to 30 nanometers and up past 3 millimeters, actually. You can measure a lot of different types of samples on it: powders, suspensions, emulsions, pastes, and creams. It's so fast that you can do very high throughput, hundreds of samples a day, either through manual measurement or through some sort of conjoined auto sampler or slurry sampler. Because the measurement's also very fast, you can try and do some dynamics measurements too. If you want to try and capture a reaction that's maybe takes a few minutes or a few hours, you can do that in laser diffraction. We have a user here in California that was studying algae growth. And what he did was he put the starting material in the analyzer, took a few measurements, initiated the reaction by adding some other materials, and then just set up a sequence so that he got a measurement every 5 minutes for 24 hours. And he can see very quickly, well, over the course of a day, I suppose, he can get very valuable information on how this algae is growing. But, that's sort of a long time scale. If your time scale is only, 45 seconds or a few minutes, the modern analyzers now can capture a full distribution measurement in less than 10 seconds. So you can capture some dynamics. Again, it's very easy to use. Modern instruments now have to be highly automated to compete and to be attractive. And the best instrument should come with some sort of self-guided software to be able to, and it's all about troubleshooting. When you run into a problem, you want to be able to self-medicate, so to speak, right? You want to be able to understand what the problem is and fix it yourself rather than relying on the vendor, which may not be able to respond to you, as quickly as you'd like. And most people want instantaneous responses, right? So it's easier if it's just popping out of the software. If the instrument is well designed, it should have very, very, very good precision. And really why precision matters is that it reduces unnecessary downtime. If you have multiple instruments or multiple operators or even multiple labs, you want to make sure that the same material produces basically the same answer. And that's really what I mean by precision here. If it's not producing the same answer and it's because of the instrument, you're going to be wasting a lot of time investigating, is this really the same material? Are my procedures good enough? Are the operators doing what's correct? All sorts of different things. But if the instrument is really well designed, you can remove that as a possible source of error and really shorten your investigation. I would call it unnecessary investigation. Again, it's a first principle measurement. No calibration is necessary. It gives you a little bit better peace of mind in the results. You don't have to teach the analyzer what the correct answer is. It either knows it or it's broken. And it's globally established on a massive scale. There are tens of thousands of laser diffraction users the world over. It is universally recognized as the most common, most popular modern sizing technique. Chances are, if anyone else in your company or your university is doing particle size analysis, they probably have a laser diffraction instrument. So that's really the end of the presentation. I would like to invite you that if you want more information, there are a lot of different resources I have up on the screen right now that you should definitely check out. The ISO guideline is perhaps probably the first place you should look. It's certainly the definitive guide to what makes a good laser diffraction measurement. And it was very recently updated in 2009, so what you should do is look at ISO 13320 2009. Eventually, when you look at the slides on our website, it'll be in a PDF, and all of these areas will be active as hyperlinks. Otherwise, you can just go to Google and type in these same search phrases and get exactly to where you need to go. Excuse me, I had a little coughing fit there. I'd also like to recommend a book by Henk Merkus. He's one of the titans in the industry. And just recently he updated his book called Particle Size Measurements, Fundamentals, Practice, and Quality. You can find it on Amazon. You can find it through Springer, a bunch of different places. Again, The link will become active when you look at the PDF version of the slides. And on our own website, we have tons and tons of resources. Again, you can access the website at horiba.com/us/particle. But we have a lot of different previously recorded webinars about laser diffraction, including one on what the current performance standards are, more information about the LA950 Method Expert software, basic information on how to understand and interpret your results, how do you set good attainable size specifications. This is probably, if you already own an analyzer, this is probably the one you should definitely watch, because a lot of users are walking around, not walking around, it's a poor choice of phrase, a lot of users have very difficult size specifications, and it's making their lives unnecessarily difficult. So we make a lot of good recommendations in this webinar on how you can help fix that. And last but not least, we have a 6-part webinar training course we call our boot camp for laser diffraction. All of this up on the website. We also have a lot of different application and technical notes, instruction manuals, software downloads. But if you'd like to ask us any questions directly, you can always reach us at labinfo@horiba.com. I think there's only 6 or 7 people that get lab info, so there's always someone on the other end. I also invite you to keep reading our monthly email newsletter. A lot of you signed up because you get the newsletter, but I know a few of you in the audience don't get it. I'd recommend it, not only because I'm usually the person who puts it together, but we really do try and put useful information there. If it's not very useful information, let me know what you'd like to see. We're always looking for suggestions on what to add. What I think is interesting or compelling or funny. As my wife often tells me, many people don't think is interesting or compelling or funny, especially not the funny part. So I'm always open to suggestions. And also on the website, we have an area called the Download Center that you'll be able to look at in a few days to find the video and slides from this presentation. So I think I've gone on long enough for the presentation. I'd like to thank you all for attending, and we'll start our Q&A section. So let me look back now at the questions area. My mouse isn't playing nicely. Bear with me for a second. All right. All right. I apologize in advance if I don't pronounce some of your names correctly. My last name is Trevoranis, which is very, very difficult to pronounce, so I usually do care a lot about pronunciation, but obviously it's hard just by looking at the text. So Jagdish is asking, if there are nano-sized and micron-sized particles present simultaneously, can laser diffraction give a reliable distribution of these? In other words, is there a weighting you have to do? That's an excellent question. And the answer I'd give is yes, laser diffraction can give you a reliable distribution, but as I was just saying, you have to remember that it's on a volume basis. So it will, in a way, weight the coarsest particles, the micron-sized particles, because it's a volume relationship, and the volume of those micron-sized particles is much, much larger than the volume of the nano-sized particles. But there's nothing about laser diffraction. The physics of it, the mathematics of it, allow us to resolve differences in discrete size distributions. Typically, we say that it needs to have a 3-to-1 size difference. So if you have a 300 nanometer distribution and a 900 nanometer distribution, it should be able to pick out the differences. Depending on the scattering efficiency, depending on the narrowness of the size distribution, the actual particle size distribution, if it's very narrow, the instrument can do a better job at picking out the individual peaks a little bit better. But this again is where diffraction is resolution limited. If the peaks are too close to each other, it's very hard to resolve. But certainly if nano-sized and micron-sized particles are present simultaneously, the instrument should be able to pick them out. Where things get a little bit more complex is if it's not the same material, if you're mixing 2 different materials that'll have 2 different refractive indices, then you have to sort of come to a decision. Do you use one refractive index? Do you use the other refractive index? You can make a measurement, recalculate it with both, and say that when I'm using the refractive index of my small particles, that gives me an accurate small particle distribution, and then when I recalculate it with the refractive index of the large particles, then that part of the distribution becomes more accurate. Jagdish also asks how we determined the 0.05 weight percent concentration in the Cnp slurry. Just as you normally would. It's you get your little mass balance out. We have a nice analytical mass balance in our applications lab that's accurate to 5 decimal places. You just get it out, you weigh it, you're very careful about how you add it into the analyzer. I won't say that it's an errorless measurement on my part, but I feel fairly confident that if the error is that it's 0.07 weight percent and not 0.05 weight percent, the analyzer is still going to be able to pick out the difference. But I would say if there's any operator involved there, it's got to be more significant than the instrument error. Pascal asks a very interesting question. In the nanometer range, do you get better resolution and or accuracy for titanium dioxide than other materials with lower refractive indices? I say it's an interesting question because it's probably probably a little difficult to answer in the scope of this presentation. It's a better question to answer through email where we can give drawings and diagrams and offer a more complete explanation. But what I will say is that titanium dioxide, especially if you try and measure it as a dry powder, has always been one of the most difficult applications. Especially as a dry powder, I say, because the interparticular forces, when you get into the nanometer regime, are so strong. It always makes me laugh. You log on to sigmaaldrich.com and you see someone advertising. You see them advertising some material as a nanopowder. Well, there's no such thing as a nanopowder. It may be a nanosuspension, but there's no such thing as a nanopowder. They're going to agglomerate or aggregate into micron-sized particles simply because the interparticular forces are too strong for only atmosphere to overcome. So I guess the short answer to your question, Pascal, is please email me and I'll be able to provide some more references and some more information. It's a little difficult over just a microphone, though. Again, I apologize if I mispronounce, but Gabriel asks if I put the wrong refractive index, will it much affect the result? It will affect the accuracy of the result if your material is less than about 20 microns, because that's when the refraction of light through the particle becomes very significant, and that's where Mies scattering theory really differentiates itself from the Fraunhofer approximation. So if your material is less than about 20 microns, yeah, the refractive index is something you should care about if you care about accuracy of the result. If you don't care that much about accuracy, if you can accept maybe 5–10% inaccuracy, and what you really care about is the product changing in any way over time, so you're sort of monitoring your process performance, or if you're changing how you create the particle over time and you want to monitor that, then refractive index doesn't really matter. You just sort of need to be in the right ballpark. What we typically do in our applications lab is when we get a novel material in from a pharmaceutical company or from a university or from whomever, and they haven't measured the refractive index or they can't be measured, we usually just pick a generic refractive index of 1.60 and stick with that. And that way, if anything happens to the product over time or if the process changes, so long as it's consistent, the analyzer will be able to tell you that something is changing. It's when you start changing it and you're not consistent that you can't really trust the results. Gregory is asking where he can find more information about the R parameter. I believe we have a technical note up on our website that discusses the R parameter and the chi-square value. That's probably the best place you can look. It'll be in the Download Center under Technical Notes. Ryan's asking a really good question. When he uses ultrasonics, sometimes the transmittance, which remember is the amount of light that's passing through the measurement zone, unscattered, unabsorbed, basically blocked, when he uses ultrasonics, that transmittance drops out of the green zone, and the green zone is the recommended concentration range. What kind of effect, if any, does this have on the final measurements? This is actually, it's very typical, because a lot of times what you're doing with the ultrasonic is you want to increase your dispersion, improve your dispersion. And what that means is you're taking large agglomerates that may look like they're 5 microns in diameter, and you're dispersing them into 1 micron primary particles. And even though a 5 micron particle will scatter more light than a 1 micron particle, it's not that you're creating a 1 micron particle, one 1 micron particle from one 5 micron particle. You're creating many small particles, and collectively they will scatter more light than the one 5 micron particle. So essentially what's happening is, because you're not really creating more particles, you're creating them in a sense through better dispersion, they're scattering more light, so your transmitted light is falling, right? More light is being scattered. If it falls far enough, basically if you're creating enough new particles, enough additional particles, it's possible that you'll start multiple scattering, and that will affect your data, but it's not terribly likely. You really need to, especially in the LA950, you really need to drop the transmittance. If it's not a colored material, if it's not very absorptive, not very reflective, you really need to drop the transmittance down to 50, 40% transmittance to even get close to starting the multiple scattering regime. It's a good question, though, because sometimes it can be difficult to know when multiple scattering starts and when dispersion ends, because they both show up the same way. Dispersion looks like the distribution getting smaller. Multiple scattering looks like the distribution getting smaller too. But if it's just barely dropping out of the green zone, you're going to be okay. You're not that close to a multiple scattering regime yet. Hector is asking, when you have an inverted, excuse me, I have a water bottle next to me that I haven't been taking any sips of. When you have an inverted emulsion, water and oil, what is the best method or accessory to check the particle size? So if it's water and oil, you can do basically, well, I should say if it's stable at many different concentrations, so dilution's not a problem, then any accessory will work with laser diffraction. That depends more on the sample quantity and how big of a pain cleanup is going to be. Right? So if you're dispersing something in mineral oil tends to get everywhere. You want to sort of minimize the amount of mineral oil you're going to use. So whereas the regular flow pumping systems and a lot of modern laser diffraction analyzers tend to be 100 milliliters and above, typically 200 milliliters and above. There are certain accessories like the mini flow for the LA950 that drop that volume requirement to 40 or 35 millimeters. Or if you can get away with the manually using the fraction cell, you can drop it to 10 milliliters and reduce your exposure to basically you reduce the cost of purchasing more mineral oil, you reduce the chance that it's going to get everywhere. If you're not so lucky as to use mineral oil, and if you have to use something like methyl ethyl ketone or something that's very strongly carcinogenic like benzene, you may also want to reduce your solvent quantity just so that you can reduce your health exposure. But I keep giving long answers to simple questions. Let me give a short answer to this question. If it's stable at multiple concentrations, it doesn't really matter. It's your personal preference. If it's not stable at multiple concentrations, then you have an option to measure with diffraction, in which case you should try and measure as fast as possible, because if it's not stable at different concentrations, then what's going to happen is it's going to coalesce and the size is going to change over time. So you want to be able to measure as fast as possible so that it doesn't have that much opportunity to change or coalesce. Or you give diffraction a miss altogether and go to another technique that can measure at full concentrations, like acoustic spectroscopy. We do have an accessory we call the PACE cell. that, again, you don't need to dilute, but it's not really applicable for water and oil emulsions. Or I should say it's only really useful if the viscosity is high enough. I mean, there's a reason it's called the paste cell. The viscosity needs to be so high that it doesn't just leak out between the two optical glass plates that we use to create the cell. I'm sorry that I keep coughing into the microphone. It sort of is surprising me too. Jagdish asks, how does the diffraction technique, excuse me, I'm not sure I understand the question. How does the diffraction technique consistent with light wavelength and particle size being about the same? Oh, okay. I think I understand. When the particle size and the wavelength of light that you're using to investigate the particles are about the same size, I wonder if you're asking how useful is laser diffraction or how reliable is it? And it is a bit of a challenge when the particle becomes very similar to the wavelength of light. I can tell you that it was a much bigger technical challenge, several generations of analyzers ago. Now the signal-to-noise ratio is so good that you can extract a lot more useful information, even when you run into the physical limits of the technique and the physical problems of the technique. Again, it's a hard question to answer in this format. We can continue the discussion through email offline, but if in the LA950 we use a 650 nanometer red laser diode, if you give me a 650 nanometer standard, the LA950 should be able to hit it right on the nose. So that's really what some of these questions boil down to. Is I can give you a theoretical explanation. I can sort of give you my best guess, but it's really the proof is in the pudding. If the analyzer can't give you the right answer at sizes near the wavelengths of light being used, then it's just so much more talking on my part. Hong Sun asks a question. If you measure a mixture that has two parts blended together, can you see two separate particle size distributions? Yes, it gets back to the resolution that I was talking about earlier. If they're sufficiently different in size, you should be able to resolve both distributions. Additionally, Hong Sun asks, if one part will absorb the light, how will it affect the total particle size distribution? Now that's another good question and somewhat difficult to answer too, because it depends on how much of the light is being absorbed. If I was going to be measuring a mixture of titanium dioxide and carbon black, and the physical size of the particles were separated far enough that resolution wasn't a concern, then I would also care about the size a little bit because, well, titanium dioxide and carbon black, maybe it's a good example, but maybe not for what I was about to say. What I was going to say was, if the particles are large enough that it's really only the red laser that's doing the investigation, then you have to care about the color. If they're both small enough that it's only the blue light that's doing the investigation, then again you have to care about the color. But in the case of titanium dioxide being sort of water white and carbon black obviously being black, neither of them are really colored in that sense, and they'll react about the same way, more or less, to the blue light and the red light. Again, I'm sort of rambling. I apologize. It's about lunchtime here, and I operate best on a full stomach. All right, let me restart. I don't like to ramble, even though I do it so often. Yes, if one component is absorbing light, it can affect the total particle size distribution. If it absorbs so much light that it is effectively invisible, then it won't appear on the particle size distribution. If you're measuring a material that doesn't absorb at all, mixed in with a material that absorbs quite a bit, then effectively it'll be like weighting the distribution towards the particle that does not absorb, because the analyzer is effectively seeing more of those particles because more of the light that's interacting with them is being scattered to the detectors. The absorbing particles are going to obviously absorb some percentage of the investigating light, which means that the amount of scattered light will be less and it won't be a true reflection of the total volume of the particles. There, I think that was reasonably coherent and to the point. All right, well, the questions are slowing down, but those of you who I haven't been able to get around to, I promise I'll get to you in email, but I think this is a good stopping point. I'd like to thank everyone again for joining me today. I really hope you found the information useful, and I hope you found the presentation to be enjoyable. It's something that I like to talk about. I would also like to ask you that when you leave the presentation, you'll be presented with the option to take a survey. Surveys aren't always the most interesting things to take, but I would appreciate it if you just took a few minutes and gave some basic responses. We do look at them. We do use them to make decisions about how we should change the webinar program in the future and how we can add some more interesting things to it. It's very useful at all times for us to get some feedback from you, so I'd appreciate it if you just took a few minutes to do it. Otherwise, I hope you all have excellent rest of the day. I'm going to, I think I brought a salad. That's not so very exciting, but anyway, I'm going to go have some lunch. So any more questions, feel free to email me, and we'll be in touch. Thank you. Bye.